Good morning. In the last lecture, we have seen that a practical single phase transformer like this supplied from a single phase constant frequency AC source and connected to a load on the other side drawing current I1 from the primary and supplying a current I2 on the secondary can be modeled using a ideal transformer along with other passive components that represents the non-ideality of the transformer. This is the ideal transformer. The non-idealities to be included are a core loss resistance, a magnetizing resistance, the leakage reactance in the primary side and the winding resistance of the primary side. Similarly, a leakage reactance on the secondary side and the winding resistance of the secondary side. This is the load. This is the output voltage V2, this is secondary resistance R2, this is secondary leakage reactance JX2, this is the primary leakage reactance JX1, primary winding resistance R1, core loss resistance R0, magnetizing reactance JXM. So, it draws, it is connected to a constant voltage, constant frequency source V1, draws a current I1 from the primary side, the no load current is I0 and sends out a current I2 on the secondary side, the turns ratio being N1 is to N2. This is the model of a practical single phase transformer incorporating an ideal transformer. This is the ideal transformer. We have also mentioned that this model is not very convenient for applying all the circuit analysis tools that we have learnt in our electrical technology class, since there is a isolation barrier at the ideal transformer, which means we cannot, for example, choose a loop current across the primary and secondary, since we do not know the voltage drop between the primary and the secondary winding of the ideal transformer. Therefore, we said that this can be converted to a convenient equivalent circuit by either referring whatever is there on the secondary side to the primary or referring the primary to the secondary side, which results in two equivalent circuit which are very closely related as follows. The equivalent circuit referred to primary will look like this. The elements on the primary side do not change. So, they retain their value. However, the elements on the secondary side has to be referred to primary with the given turns ratio. So, primary voltage will still be V1, primary winding resistance will be R1, leakage reactance will be Jx1, core loss resistance and magnetizing reactance are also generally referred to the primary. So, this will remain R0, this will be Jxm. The primary current will be I1, no load current I0. The secondary current I2 will now be replaced by I2 dash given by N2 by N1 into I2. The secondary leakage reactance Jx2 dash is given by N2 by N1 by N2 square Jx2. Similarly, the referred secondary winding resistance R2 dash will be given by N1 by N2 square R2. The load impedance ZL dash, the referred load impedance ZL dash will be given by N1 by N2 square ZL, and the output voltage, referred output voltage V2 will be V2 dash will be N2 by N1 into V2. I am sorry, N1 by N2 into V2. So, this is the exact equivalent circuit. Why we are using the term exact, we will come later on, of the single phase transformer referred to the primary side. Of course, this equivalent circuit can be drawn referred to the secondary side as well, and that circuit also we have shown the other day. It is in that case the secondary elements are not changed, but all the primary elements are referred to the secondary by the turns ratio. So, now the secondary load impedance ZL remain as it is, winding resistance remain as it is, leakage reactance remains as it is, the current I remains I2, the load voltage remain V2. However, the primary side elements, for example, the magnetizing reactance now Jxm dash will be equal to N2 by N1 whole square Jxm, R0 dash will be equal to N2 by N1 whole square R0, I0 dash will be equal to N1 by N2 into I0, the primary winding resistance R1 dash will be equal to N2 by N1 whole square R1, primary leakage reactance J X1 dash will be given by N2 by N1 whole square X1, and the source voltage V1 dash will be equal to N2 by N1 V1. So, these are the two equivalent circuits. The first one is referred to the primary with number of turns N1, the second one is referred to the secondary with number of turns N2. Now, the major application of these equivalent circuits are in determining the different variables. For example, if V1 is given, the load parameter is given and the circuit parameter is given, then we can find out all the currents, the voltage, etc. Let us look at a concrete example. Let us say that this is a single phase transformer, the ratings are 230 volt is to 115 volt and the kVA rating is 3 kVA, which means N1 is to N2 for this case is 2 is to 1. Also, let us say the load impedance is actually a load resistance of value 3.75 ohm. The other parameters R1, say it is given as 0.75 ohm, X1 let us say it is J 0.8 ohm, R0 given to be 600 ohm, Jxm is given to be 300 ohm. Similarly, X2 dash, X2 rather is given to be 0.15 ohm and R2 is given as 0.125 ohm. The problem is to find out what will be the load terminal voltage V2, what will be the load current I2, what will be the current drawn from the source I1 and what will be the no load current I0. How are we going to solve this problem? So, as a first step, let us draw the equivalent circuit referred to primary. The source voltage is given to be 230 volt 50 hertz single phase. So, let us draw the equivalent circuit of the transformer referred to primary. J 0.8 ohm. Since we have referred it to the primary, it will be J XL2 X2 dash and its value will be 0.6, since the actual value referred to the secondary was 0.15 ohm and N1 by N2 is 2, therefore, X2 dash will be 0.15 into N1 by N2 square, which is 4, and hence 0.6 ohm. Similarly, R2 dash will be 0.5 ohm and RL dash will be equal to 15 ohm. The output voltage is V2 dash, output current is I2 dash, input current is I1, input voltage is 230 volt, 50 hertz. So, let us take it to be our reference phasor at 0 degree. The magnetization branch is referred to the primary, so its values do not change. This is 600 ohm, this is J 300 ohm. Now, there are different ways of solving this circuit, for example, the loop current method or the node voltage method. However, for this particular problem, we will apply the Thevenin's theorem. So, let us find out the Thevenin equivalent circuit at these two terminals looking back. The V Thevenin at these two terminals is given by impedance here divided by the total impedance into the voltage, that is 600 parallel J 300 divided by 600 parallel J 300 plus 0.75 plus J 0.8 into 230 angle 0 degree. Now, 600 parallel J 300 is equal to 120 plus J 240. Similarly, the denominator becomes 100 600 parallel J 300 plus 0.75 plus J 0.8 becomes 120.75 plus J 240.8, which is equal to 269.38 angle 63.37 degrees, and this is 268.33 angle 63.43 degrees, and VTH is, if we calculate, comes to be 229.1 angle 0.07 degrees. So, what is ZTH? ZTH will be the equivalent impedance seen at this terminal when the input source is shorted. Therefore, ZTH is equal to 600 parallel J 300 parallel 0.75 plus J 0.8. In other words, ZTH equal to 120 plus J 240 parallel with 0.75 plus j 0.8, and if this is computed, ZTH comes to be 0.7461 plus j 0.7978. So, what will be I2 dash in this circuit? I2 dash will be, so what is the Thevenin equivalent circuit? Let us first see. The Thevenin equivalent circuit becomes VTH in series with ZTH in series with rest of the circuit. Please note that if this voltage in the actual circuit was E1, the voltage at this terminal will also be E1. Since E1 equal to I2 dashed into this complete impedance, here also E1 equal to I2 dashed into this impedance, and this impedance do not change because only the input side has been changed. So, what will be I2 dash? I2 dash will be equal to V Thevenin divided by Z Thevenin plus sum of these impedances, which is 15.5 plus j 0.6. This will be equal to 229.1 angle 0.07 degrees. That is what we have found for VTH previously, and the total impedance will be 16.2461 plus j 1.3978, and this comes to be 14.05 amperes at an angle of minus 4.85 degree with respect to the primary applied voltage. Now, I2, how much is I2? I2 equal to N1 by N2 into I2 dash, hence I2 is 28.1 ampere at an angle of minus 4.85 degree with respect to the input applied voltage. Therefore, we have found answer to one of the problems, that is, we have found what is the output current. So, what is the output voltage? For that we will calculate what is V2 dash. V2 dash is nothing but I2 dash into load resistance. And this comes to 210.75 volts at an angle of minus 4.85 degrees with respect to the input applied voltage. What is V2? The actual load voltage. V2 equal to N2 by N1 into V2 dash, hence it is 105.375 volt angle minus 4.85 degrees. So, this is the answer to the second part of our question, what is the load voltage. How do we find out the magnetizing current? Please note that we have already argued that if the voltage at the air gap, this is called the air gap voltage, is E1 in the actual equivalent circuit, then in this Thevenin equivalent circuit also the voltage will be E1. So, let us try to find out what is E1 first. Now, E1 from this Thevenin equivalent circuit is I2 dash multiplied by the total impedance of the secondary side. These are all phasors. And if we calculate, this comes to 217.94 volts at an angle of minus 2.633 degrees with respect to the primary applied voltage V1. So, what is no load current I0? I0 is E1 divided by 600 parallel J XM, that is from this actual equivalent circuit. Hence, if we compute I0 will come to be 0.8122 ampere at an angle of minus 66.07 degrees. This is the phase angle with respect to the primary applied voltage V1, since that is what we have assumed to be our reference phasor with angle 0. What is I1 then? Obviously, I1 is the phasor sum of I2 dash and I0. It should be noted that the current supplied by the Thevenin source is not I1, it is I2 dash. So, therefore, to find out the source current I1, we should go back to the original equivalent circuit where before we took the Thevenin equivalent circuit. Therefore, I1 is given by I2 dash plus I0, phasor sum of I2 dash and I0. That is, we have found out I2 dash to be .05 ampere angle minus 4.85 degrees and I0 to be 0.8122 ampere angle at minus 66.07 degrees. Therefore, if we do the computation, I1 will come as 14.458 amperes angle minus 7.67 degrees. So, that shows how to use this equivalent circuit to compute different variables, voltages and currents at different parts of the transformer. And it will be interesting to solve the same problem using the equivalent circuit referred to the secondary, but this is left as an exercise. However, the purpose of solving this problem was not just to show how this problem can be solved. I would like to draw your attention to a few salient features of this equivalent circuit. For example, let us see the applied voltage. The applied voltage was 230 volt at an angle of 0 degree, while when we computed the Thevenin voltage, it comes to, when we compute the Thevenin voltage, it comes to something like 229 point, the Thevenin voltage comes to 229.1 volt, angle 0.07 degrees. Now, is this very different from the actual applied voltage? Similarly, the Thevenin impedance ZTH comes to 0.7461 plus J 0.7978. If we look at the actual primary impedance, it was 0.75 ohm and 0.8 ohm here. Therefore, it possibly makes sense, in order to reduce the computational complexity, to obtain this Thevenin equivalent circuit by simply omitting this part and connecting this right across the supply voltage. In fact, that is what is done in most practical cases, since the results that are obtained by that approximation is not very different from this exact equivalent circuit. We will shortly see that. The rationale is this impedance of the magnetizing branch being much higher than the impedance of the primary winding, that is winding resistance and leakage reactance, the entire applied primary voltage appears almost across the magnetization branch. The drop across the primary impedance is very small even at rated current. With that assumption, the exact equivalent circuit referred to the primary can be simplified by the following approximate equivalent circuit. Here in the approximate equivalent circuit, the magnetization branch is connected right across the source, and the primary impedance and secondary impedance are connected together. V2 dash, load current I2 dash. Please note, this was the exact equivalent circuit. In order to get the approximate equivalent circuit, what I have done, I have simply shifted this magnetization branch from this middle point to the beginning, that is right across the source, to get the approximate equivalent circuit. The underlying assumption being the drop across the primary winding impedance is very small compared to the total applied voltage. Now, this can be further simplified, and the resistances can be clubbed together and reactances can be clubbed together to give a even simpler form of the same equivalent circuit. That is equal to R1 plus N1 by N2 square R2 and J x eq equal to J x1 plus x2 dash, that is equal to J x1 plus N1 by N2 square x2. This remains Z L dash, the current is I2 dash, this voltage is V2 dash. The primary current is I1, magnetizing current is, the no load current is I0. Obviously, this circuit, this approximate equivalent circuit is far simpler compared to the exact equivalent circuit that has been shown earlier. Now, how much error would we incur if we use the approximate equivalent circuit instead of the actual equivalent circuit? Let us try. Let us try with the same problem. So, the approximate equivalent circuit for the earlier problem will be this is 230 volt, angle 0 degree. We have to find out this current I1, the no load current I0, Req from the given data is equal to 1.25 ohm, Xeq from the given data is J 1.4 ohm, the load resistance RL dash equal to 15 ohm. This is referred load voltage V2 dash, this is the referred load current I2 dash. So, how do we compute I2 dash here? I2 dash is simply equal to 230 angle 0 degree divided by 16.25 sum of these impedances plus j 1.4, this is given by 14.1 ampere angle minus 4.924 degrees. So, I 2 equal to N 1 by N 2, I 2 dash is 28.2 ampere angle minus 4.924 degrees. What is V 2 dash? V 2 dash again is 15 I 2 dash and the value is 211.5 volt angle minus 4.924 degrees, and V 2 equal to N 2 by N 1, V 2 dash equal to 105.75 volts angle minus 4.924 degrees. The simplification in the calculation is very apparent. We do not have to find out the Thevenin equivalent voltage or Thevenin impedance, we can simply calculate the variables. I 0 and I 1 can be computed similarly. I 0 equal to 230 angle 0 degree divided by 600 parallel j 300, and is the value is 0.8571 amperes at an angle of minus 63.435 degree with respect to the applied voltage phasor. The input current I 1 is the phasor sum of I 0 plus I 2 dash, and after computation it value comes to 14.566 ampere angle at minus 7.8 degrees. So, the amount of simplification in computation is very apparent. So, let us compare the accuracy. So, this we can do by drawing this table. So, let us see, this is the variable name. Next, let us put the exact equivalent value from the exact equivalent circuit. Then value from the approximate equivalent circuit. And percentage error, let us say only in magnitude. The first variable, let us take the load voltage V 2. The value we have got by exact equivalent circuit is 105.375 volt at an angle of minus 4.85 degrees, and from the approximate equivalent circuit we have got it to be 105.75 volts at an angle of minus 4.924 degrees. The percentage error in magnitude, which is this value minus this value divided by this, comes to minus 0.356%. For I 2, the magnitude was 28.1 ampere, angle was minus 4.8 degrees. Here the magnitude was 28.2 amperes, angle was minus 4.924 degrees. So, again the percentage error in magnitude is just 0.356%. What about I0? The magnitude by exact equivalent circuit came to be 0.8122 ampere at an angle of minus 66.07 degrees. By approximate equivalent circuit it came to 0.8571 amperes at an angle of minus 63.435 degrees. The percentage here error here comes to be minus 5.53%. Lastly, for I1, the magnitude came to be by exact equivalent circuit it came to 14.458 ampere at an angle of minus 7.67 degrees, and by approximate equivalent circuit it came to 14.566 amperes and angle of minus 7.8 degrees. The percentage error is just minus 0.747%. Now, we have already seen how much simplification in computation can be achieved if this approximate equivalent circuit is used, and this table shows the kind of accuracy that we can expect. We see that in most cases the percentage error is less than even 0.5%, except for the in the value of the magnetization current. The magnetization current itself is less than 5% of the rated current. That is why this value comes slightly higher, but even then that is close to 5%. Hence, for all practical purpose in a transformer, it is normally this approximate equivalent circuit which is used, and until and unless it is absolutely necessary, the exact equivalent circuit normally is not used. Now, the approximate equivalent circuit can also be referred to either primary or the secondary. For the primary, we have already shown the approximate equivalent circuit to look like this. However, this can also be referred to the secondary side, then it will look like sorry. Where V1 dash is equal to N2 by N1 into V1, V2 dash equal to N1 by N2 V2, I2 dash I2 dash equal to N1 N2 by N1 into I2, I1 dash equal to N1 by N2 into I1. For the variables Req dash, Req equal itself is R1 plus R2 dash Xeq equal to X1 plus X2 dash, Req dash equal to N2 by N1 square Req, hence it is equal to R2 plus N2 by N1 square R1 equal to R1 dash plus R2. Similarly, Xeq dash equal to N2 by N1 square Xeq equal to X1 dash plus X2. R0 dash equal to N2 by N1 square R0 and Xm dash equal to N2 by N1 square Xm. Therefore, in order to solve a given transformer problem, the approximate equivalent circuit will normally be used. The approximate equivalent circuit can be either referred to the primary or referred to the secondary. The relationship between the variables and the equivalent circuit parameters are given by these equations.